So in this session, I'm going to be looking at essentially optimizing with the compiler. So I'm going to look at the sorts of things that the compiler can and should be doing for you in terms of optimization, and some of the reasons why some code won't optimize well, and a bit about what you can do about it. And also look at a few specific compiler options for the compilers that are available on Archer 2 as well. I won't talk about vectorization in this talk. That'll come tomorrow. So Adrian will do a session specifically looking at vectorization tomorrow. So some of the same issues apply there, in the sense that vectorization is something that the compiler has to do for you, and essentially our job as programmers is to try and potentially try and modify the code to make it easier for the compiler to do its job. That's true for other types of optimization as well, and that's really what I'm going to cover in this session. Okay. So just by way of introduction, so obviously unless we're going to handwrite assembly code, we're always using a compiler, and modern compilers are really quite good at optimization, at least for restructuring code. They're less good at restructuring for memory optimizations, and again, we'll talk more about memory tomorrow. On the whole, it's much better to try and get the compiler to do the optimization for you. It avoids you doing specific coding, and compilers are not infallible, but they break codes much less often than humans do. And even if we are modifying code, then we can think of that as trying to help the compiler, because the compiler is still there. And it's useful to think of it that way, as code modifications are what you do to help the compiler do its job better in many circumstances. So some basics about compiler flags. So a typical compiler has hundreds of flags and options, most of which you'll never use and most of which are not related to optimization. But most compilers have flags for different levels of general optimization. Typical series of -01, -02, -03, etc. However, compilers differ quite a lot in what they do at different optimization levels. So -02 in one compiler does not mean the same as -02 in another compiler in terms of which optimizations it's going to attempt, and it actually can be quite tricky to figure out from the documentation exactly what a given one of these optimization levels actually does, actually expands to. I mean, you can sort of turn on verbose mode and look at what the compiler is really generating with low-level flags and so on, but it requires a fair bit of digging to figure out whether -02 is doing a particular optimization or not, for example. Okay, so this is probably not news to anybody, but when you're first porting a code, it's a good idea to switch your optimization off. Test it to make sure it works, then turn your optimization on and test it again. But obviously, don't forget to use them. Okay, so don't leave out the optimization flags if you're doing anything that's performance critical, on obviously. But also, when you come to once you're satisfied everything's working okay, don't forget to turn off all your debugging, bounds checking, profiling flags, and so on. Because they can all affect performance negatively. Okay, a warning: the highest levels of optimization can do several bad things. They can break your code. Okay. Some compilers are explicit about that, and they say, you know, minus 0.05 is not guaranteed to give you the correct results. Other compilers do it accidentally. Okay, so they try to generate correct code for a high optimization level, but they might not succeed because of bugs in the compiler. High level optimization may cause your code to give different answers because they bend standards a bit. Okay? It might particularly with floating point calculations, you might get different rounding behavior from high optimization levels. And there's also absolutely no guarantee that turning up the optimization level actually makes your code go any faster. So always read the documentation carefully. So know what you're potentially exposing yourself to with high optimization levels. And if you find that something does give you a problem, then you may wish to only apply a very aggressive optimization selectively to certain files. So if you find that if you turn high level optimization on for your whole code and you get the wrong answers, then obviously you can just back it off. But it may well, there's a good chance that the thing that's breaking is not necessarily performance critical. So you may be able to figure out which routines are causing the problem. That can be tedious. You can do things like compile half your files with optimization and half without, and see if that works, and continue doing some sort of binary chop operation until you figure out which file which file or routine is breaking, and also depending on the code base you're working with, having relatively few, maybe one routine per file is excessive, but not having files with 50 different functions in it might be helpful. Other things to be aware of: many compilers are designed for an instruction-set architecture, not one particular instance of a machine. So there are often flags to target different instruction set architecture versions, different processor versions, potentially even different cache configurations. So you just need to be aware that the defaults may not be optimal, especially if you're cross-compiling. So that means if you're compiling on a processor which is not the same as the processor that you're intending to run on, then you need to think about whether the compiler is picking up the default options for the processor that the compiler is running on, and those might not be optimal for the processor that you're intending to run on. Okay. Thankfully, no such problem on Archer 2. The login node are the same processor, the same AMD ROM processor as the compute nodes. There may well be some optimization flags which are not part of the -0123 sequence. There's usually a good reason for that. So check the documentation and use them sparely. There probably is the probable reason that they're not part of the standard sequence is that they're only beneficial in a small number of cases, or that they sometimes make things go slower rather than faster. So that's you want to use those relatively sparingly, probably. Okay. Other things, so that's flags. Other things we can use are compiler hints inside the source code. So this is a mechanism for giving some additional information to the compiler. So things like values of variables, independence of loop iterations, independence of index array elements. So if you have an array indirection, you can tell the compiler that all no two values in this index array are the same, for example. Things like aliasing properties. So I guarantee that that these two names will move into the same. So these things are for trying to preprocessor pragmas in C or C++. So they're not directly code modifications in that sense. They don't affect portability. Other compilers will simply ignore them. So compilers compilers are limited in what they can do, partly because they have limited information available to them. Most compilers work in an incremental fashion in the sense that each source file is compiled independently of each other. And they make routines they make worst case assumptions about what's going on in routines which are in other source files. So they can, the compiler can see the routine prototype. It makes the worst case assumptions about what those routines might be doing to their arguments or to global variables or whatever. So you can help by providing more information. So particularly things providing information via routine prototypes. So you can use intent in Fortran and pure. You can use const in C and C++, to indicate that the value of a function argument is not going to be modified. There are also hints and potentially also command line flags that you can use to tell the compiler, please also look in this other file to do inlining, for example. These days, compilers also tend to do a bit more work in terms of optimization at link time. So this is so that helps obviously, because at link time the compiler can see all the code and do things like cross procedural optimizations at link time. So that's all great, but probably sooner or later, if flags and hints don't solve the problem, then we may have to resort to code modification. But think carefully before you go down this point. You have to be aware that this can introduce bugs. It can make your code harder to read and maintain, particularly for other people. And it may only be effective on, for certain architectures and certain compiler versions. And so what I want to encourage you to do is try to think about, what optimization do you think the compiler is failing to do, and what additional information can you provide it, and how can rewriting help the compiler do its job better. So how do you work out what the compiler has done? Well, if you're brave and familiar with assembly code, you can look at the assembly code. Okay? But that's hard and scary. The other thing you can do is use diagnostics flags. So many compilers support flags which will try to tell you something about what the compiler has done. So it produces, often sometimes these are annotated source code. Sometimes it's just a list of, with line numbers saying, okay, loop at line, loop in function blah at line 273 was unrolled to a depth of 4, whatever. So you can get the compiler to emit some compilers to emit information like that. So compilers do vary a bit in what they're able to give you here. that's fine. It's just also worth bearing in mind that it's, these days it's increasingly difficult to work out what actually, even looking at assembly code only tells you so much, because it's hard to work out what actually occurred in the processor because of all this stuff that I talked about earlier that's going on. You've got superscalar issue, you've got out of order, speculative execution, all this magic going on in the hardware, which you can't see, can't diagnose, can never know effectively, essentially. You can maybe do something with eyeballing assembly code. You can count types of instructions and see whether the performance you're getting is what you expect. But that's quite specialized and difficult, and is certainly not for everybody. Okay, so I want to run through a few different topics where we're to look at things that can cause compilers problems, in terms of trying to understand what the compiler is trying to do and the things that can prevent it. So first one is really locals and global variables. Because the compiler is essentially working one routine at a time, and the compiler analysis is always more effective with local variables, and it has to make some worst case assumptions about global variables. So in that, they could be modified by any called procedure or potentially by another thread. So it's worth using local variables where you can. And some people worry about local variables causing performance loss, but automatic variables are stack allocated, and their allocation is essentially free. So if you declare variables, local variables inside a subroutine or a function, then the actual allocation of those variables is done on the stack. So that's already pre-existing allocated memory space, and it just involves moving the stack pointer, and it's essentially free. So you shouldn't worry about the cost, any cost associated with declaring variables locally inside routines. And in C or C++, if you want to use global variables, try to keep them at file scope, because again, then the compiler is working with that file. It can see them, and it can work out what's being done with them. Okay, so next topic is conditionals. So even if we have fairly sophisticated branch prediction hardware, then branches are still bad for performance. And they're bad because they inhibit the compiler from doing a lot of the important optimizations. And so we really want to try and avoid having branches in innermost loops if we can. So if you eliminate them entirely, at least try to get them out of the critical loops. So for example, if something like this, you'd maybe hope the compiler does for you, because the loop in the code on the left, the test if n equals 0 is independent of the loop. So it's the same test for every loop iteration. So you might hope that the compiler spots that and moves the test outside the loop. But not all things are that easy. So this is a more difficult example. So if I is less than j, do something else. Then explicitly splitting the loop into two pieces might be better, so that you can so that the compiler so you essentially eliminate the condition altogether, and the compiler doesn't have a hard job of figuring out what to do. Okay, data types. So your choice of size of data types can affect the performance. There's a difference between 32-bit and 64-bit arithmetic. So if you can, obviously numerically your algorithm may not be able to tolerate anything less than 64-bit, in which case, fine, okay. If your numeric algorithms are not so numerically sensitive, then you might want to ask yourself, well, can I use 32-bit? That might help, particularly with again, I'll leave vectorization for tomorrow, but obviously you can get twice as many instructions in a SIMD operation if you're using 32-bit versus 64-bit. But it can be complicated with trade-offs with memory usage and cache usage and so on. Another thing to be aware about is to avoid unnecessary type conversions if you can. The compiler will always do what you asked it to do in terms of types. Okay, so the compiler is not going to change the types for you. And obviously, depending on the language, some type conversions are implicit. But sometimes sometimes you can't avoid it. But type conversions consume instructions and make the compiler's job more difficult. Next one is CSE, which stands for Common Sub-Expression Elimination. So this is where in your code you do the same statement or part of a statement twice, and so you hope that the compiler can spot that and only do it once. Things where they have trouble. Well, if the order of operands is different, then in the first case here, then if this is floating points, then depending on the level of optimization, the compiler may decide that it's not allowed or it won't compute A plus C once here. Worse though is function calls. Okay, so if you have a repeated function call, then it can be very difficult for the compiler to work out that the function call those two function calls are going to return the same value. Because in general they don't. Okay, so if func is a random number generator, you sure as hell hope that it's not returning the same value. So the compiler again has to make worst case assumptions. So if you're expecting the compiler to spot that, then you have to be pretty explicit in telling it. So the compiler has to know that the function always returns the same value for the same input, and it doesn't cause any side effects. So it doesn't modify its input, it doesn't change any global data. So you need to be pretty careful with how you specify your function prototypes to let the compiler know that kind of thing. Okay, register use. This is getting increasingly less important with modern processors with very large register files. So it's still possible that they can run into problems if you have implicitly very large blocks of code. So if you have loops with very large numbers of temporary variables in it, so those may not be that. It may not look like that in your source code, but if once the compiler is done inlining and loop unrolling, then you can end up with a lot of temporaries or array elements with complicated index expressions and so on. You can sometimes help the compiler by putting explicit scalar temporaries in your code. So most compilers will use a register for an explicit scalar in preference to an implicit common sub-expression elimination. Okay, so it's an example here where essentially introducing a temporary may help. Okay, so you've got this basically this indirection here. So and then reassignment to C. So this can cause this kind of thing can cause problems. But if you introduce an explicit temporary here, then the compiler can do better analysis. So if the compiler does run out of registers, it'll do what's called spilling. So it'll basically, if it runs out of registers, what it has to do is store a value into memory and then load it back in later on. It can be hard without looking at assembly code. It can be hard to figure out when this is happening. Maybe the compiler loop diagnostic tells you that it's generated some spill code. So this is typically caused by having very large loop bodies. So you may need to split up your loop into smaller pieces. Okay, so the next two things I want to talk about are loop optimizations. So this is loop unrolling and software pipelining, and they're probably the most, along with vectorization, they are two of the most important optimizations that we care about for scientific codes on modern processors. And compilers are generally pretty good at this. If a compiler fails, it's usually better to try and remove the impediment rather than doing this by hand, because it makes a terrible mess of your code if you do this by hand. Essentially, this applies to vectorization. In order to apply these optimizations, the compiler has to be able to work out that the iterations of your loop are independent. Okay, so that's the key thing. So if the compiler cannot guarantee that one loop iteration does not depend on some previous iterations, then it will not be able to generate this kind of optimization. And again, this applies to vectorization as well. So what's the problem that the compiler is trying to solve here? This is basically loops with small bodies. Okay, so if your loop contains not very much code inside it, so maybe a single statement with just a couple of floating point operations, for example, it's an extreme example. So what happens in that case is that when that block of code gets compiled, it produces a really small block of assembly code. And so that code is likely to have a lot of dependence between instructions. So that prevents multiple issue, and it can cause gaps in your instruction issue. You'll also have a fairly high branch frequency. If there's only a certain number of instructions in the loop body, then every time you go around the loop, you have to take a branch, and there's not much scope for good instruction scheduling. Okay, there aren't many instructions. There's a lot of data dependencies between them. The compiler cannot do very much. So what loop unrolling is, it's a technique for increasing the size of the loop body to both give more scope for better scheduling and also to reduce the branch frequency and make more independent instructions available for multiple issue. So what's happening here is basically the compiler is essentially replacing the loop body by multiple explicit copies of the body. Okay. And then you also have to modify the loop control and take care of the bounds and so on. And so a bit of terminology here is the number of copies of the body that are being made is called the unroll factor. Okay, so that's what your compiler diagnostics will report. It will report how many times a loop was unrolled. That means how many copies of the body have been made. So if I have a loop here on the left, if I were to do an unrolling by hand, then that would produce the code on the right here. So what's happened is I now have, instead of one copy of the statement inside the loop, I now have 4 copies. So I've got an unroll factor of 4 here. And then I have to take care of the loop bounds to go in strides of 4, and then also potentially deal with the fact that n may not be divisible by 4. So I have to have a bit of normal loop at the end to take care of iterations which are left over, the remainder that are left over at the end. So you can see that doing it by hand in your code is horrible. It makes your code very hard to read, very hard to maintain and modify. I've ended up, instead of, if I wanted to make a change to the loop body on the left, that's one change. If I want to make the same change to the code on the right, I have to make 5 changes and make sure that they're all the same. So it's a really nasty thing to do by hand. But this is the transformation that the compiler is doing for you. Obviously, it's not doing it at the source code level. It's doing it at the, well, either the intermediate representation or the assembly code level. Yeah. So this is the compiler is not doing this explicitly to your loop code. So essentially what's happening here, if the loop iterations are independent, then we end up with a larger basic block with fewer dependencies and more scope for scheduling. And we also reduce the frequency of the compare and branch instructions that are needed for the loop control. So again, the choice of unroll factor is important. If you make it too large, then you can potentially run out of registers. So again, it's good but the compiler knows exactly how many registers it's got to play with. So it's again another reason for not doing it at the source code level, but letting the compiler do it. The main problems here is that compiler, if you have some complicated flow control in there, so particularly branches or jumps, then the compiler will simply not unroll because it's hard to generate the code to jump out of the unrolled version at the right place, for example. There's a slight extension to this trick if we have loop nests, because then we have a choice. If we have, say, a doubly nested loop like the one on the left here, then it's possible to choose to unroll the outer loop instead of the inner one. And in some cases, that has an additional advantage of improving locality. Because what happens here is essentially on the right-hand side here, we can essentially only ever make sure we only ever load C once. And only ever load DJ once as well. That's the important thing here. Okay, and so this can be better in terms of if you do the counting here, we've basically got here we've got to do 2 on the left. We have to do 2 loads for every floating point operation. We've got to load A and load D. Once we've done this transformation on the right here, then we have 4 flops in the loop body, but we need 4 loads for A, but only 1 for D, because we get to reuse the DJ. Something else that can be to help break some more dependencies and improve scheduling opportunities. And this is a very close connection to reduction variables in parallel loops. So the example we'd be thinking of is the classical example would be something like this, where you're forming the sum, you're forming a sum into a scalar variable on the left-hand side. So I'm forming a sum into B here. Okay, so I can do loop unrolling on this example, but I still have dependency between a formal dependency between those two statements. The value of B that I use in the second statement depends on the value that was calculated in the first statement. But the compiler can do something to break this dependency. So it can say, okay, well, I'll actually use two different accumulators for the two different statements and to compute partial sums and then add them up at the end. Again, that can potentially change your floating point rounding behavior because you're doing sums in a different order. You might care about that. You might need to turn on sufficient, depending on the compiler, you may need to turn on sufficient level of optimization for the compiler to be okay with that kind of thing. Okay, registry renaming, I'm going to skip over this. It's not really that important and not something you can really care about too much. We'll, however, talk about software pipelining. So again, this is another technique to deal with small loop bodies, where there are dependencies between instructions in the basic block. And the idea here is that it's possible to start executing instructions from the next iteration before the current one is finished. So basically to overlap the execution of statements from different loop iterations in the same block of code. So the idea of software pipelining is to construct a basic block that contains instructions from different loop iterations, again, for fewer dependencies. We need some additional code at the start and the end of the loop in this case to make it all work properly. Okay. So again, the way you can think of this as working, and again, you would not want to do this in source code. This is purely to illustrate what's going on. And again, remember that the compiler is doing this at a lower level. So if I took the loop at the top left here, and I introduce some temporaries so that it makes so I'm really down to the level where each statement only requires, in principle, a single instruction. Okay, so if I introduce these explicit temporaries, you can see that I now have three statements in the loop. First one requires a load of A. The second one does the addition, and the third one does the store. So I've labeled those, and this is for the ith iteration. So I've labeled those Li for the ith load, AI for the ith add, and Si for the ith store. Okay. So what we can then do is change that into the code on the right, where if we look at the loop in the middle to begin with, then essentially what we do is reverse the order of the statements, but they're now coming from different logical loop iterations. So our loop body now contains the ith store, the I plus 1th add, and the I plus 2th load. Okay, and now those three statements do not depend on each other. Okay? On the left here, I have to have the ith add depends on the ith load, the ith store depends on the ith add. But in this version right here, because the statements come from different iterations which are independent, then there are no dependencies between them. In order to make this work properly, I need to get things started at the beginning by issuing the start ones, and then I need to do some cleanup at the end to get the last bits done. But that's essentially what's going on with software pipeline, is this transformation which helps to give you blocks of code with fewer dependencies in them. Okay. And basically, this is the same thing at the instruction level. Okay, so I think I won't talk through this. It's just you can see what's going on at well, with the actual instructions, but it is pretty similar. So very often you'll find that the compiler may try to do both loop unrolling and software pipelining combined for a particular loop. It depends on what the statement is inside the loop and how big the basic block is. Okay, so what can prevent this going on? So basically, function calls. If you have a function call in your loop, then unless you have unless compiler has good interprocedural analysis and inlining, and is able to deal with it, and it's a pretty simple case, then that'll prevent it. Any sort of conditionals, especially if control transfer goes out of the loop, and you lose most of the benefit anyway because they break up the basic block. Another problem, pointer or array aliasing. Okay, so if the compiler cannot be sure that different values don't overlap in memory, then it cannot be certain that these optimizations can be done safely. So as a simple example here, so there's code at the top here. So basically uses this is an indirect addressing problem. Okay, so I have an indirect address into the array A here, but there's also a reference to an element of A on the right. So as a programmer, we may well know that none of the values that appear on the left-hand side ever appear so index of I never takes the value IP. Okay? But the compiler can't possibly know that. It has to assume that it might. So you can try things like hinting. So you can maybe include a compiler hint saying that index is a permutation. Some compilers support that kind of thing. Or you might be able to have a hint that tells the compiler explicitly that it's okay to unroll this loop. Tell it that the loop iterations are independent. If that fails, in this case, there is a rewrite. Okay, if you just store IP in a temporary, then it's clear to the compiler that only needs to be loaded once, and the compiler is safe to go ahead and do stuff. Inlining, okay, compilers are very variable in their abilities here. Generally, they're getting better, which is good. Again, hand inlining is a horrible thing to do. It's very ugly. You can sometimes make that less horrible with preprocessor macros, but that's still not that nice because you're basically replicating code. Okay. The problem is that the compiler has to know, in principle, where the source of the candidate routines are. So that can sometimes be done by compiler flags. You can point the compiler at, say, okay, I want you to do some inlining, and the source code for these that I care about is in these other files somewhere. Increasingly, though, this process is done at link time. but you may still need some extra flags to persuade it to happen. It's particularly important for object-oriented code, okay, because object-oriented design encourages you to write methods with very small bodies. You know, for example, getter and setter methods. The body of those does nothing except just return a value effectively from inside an object. So you can end up with very high function call overheads from OO code if the compiler doesn't do a good job. In particular, so you can use the inline keyword in C++, but you have to be aware that that's just a hint. Okay, it certainly doesn't guarantee that the compiler is going to do it. It just says to the compiler, please consider inlining this thing. But it certainly isn't a guarantee that it's going to happen. Yep. Okay. So sometimes optimizations require multiple steps. So, for example, if you have multiple levels of inlining, or maybe you need, what you really need to happen is inlining followed by loop unrolling, followed by common sub-expression elimination. And in that case, the compiler may not be able to do it all. The problem here is that internally in the compiler effectively applies a sequence of code transformations in what's pretty much a predefined order. And sometimes those are repeated, but nevertheless, if you're relying on a particular sequence of optimizations to get to the right solution, for the compiler to get to the right solution, it may not be able to get there. But again, try to minimize the changes. Look for the least damaging code change that allows the compiler to do the rest. Don't try and do, just because the compiler fails on a sequence, don't necessarily try to do the whole sequence for it. Okay, finish off a few bits and pieces about specific compiler flags on Archer 2. So there have been some significant changes to Cray compilers relatively recently. So in particular, the C and C+ compilers are now no longer Cray proprietary software. They're effectively a version of Clang. So they take all the normal flags for Clang. Cray Fortran compiler, on the other hand, is still Cray's proprietary product, and so in Cray internal product. So in particular, things to look for: optimization options. O2 is for Cray compiler, O2 is actually pretty aggressive, and O3 is seriously aggressive. Also, yep, the RA and -RM flags are ways of generating compiler diagnostic information. You get a reasonable, so probably of all the compilers on Archer 2, this is the best that you get in terms of producing sensible information about what the compiler has done or not done. And in terms of parallelization, again, this is a fairly recent change. The Cray compilers used to have OpenMP enabled by default, but this is no longer the case. You have to explicitly have the -A2MP flag these days. It does. I think I'm correct in saying it warns you if there are OpenMP directives in your code and you compile without this flag, you get a warning saying there are unprocessed OpenMP directives. Go. Okay. Yeah. So essentially, for Cray Fortran is that most is actually fine. The default value is 02, and mostly that's fine. It's actually it's actually equivalent of -03 or -fast in other compilers. And so -03 and HFP3 is seriously aggressive, but you should use that sparingly. You can also turn down specifically for floating point. If you're concerned about floating point reordering, the -HFP flag is basically a way of turning down the floating point optimizations without affecting the other optimizations that are going on. But I say don't just go aggressive. Don't just go super aggressive. It doesn't necessarily help. Yep, OpenMP, I guess, no longer on by default, so that's a change. Yeah. Okay. So on Archer 2, we have these 3 sets of compilers available. We've got the Cray compilers, GNU compilers, and AMD compilers. So GNU is GNU, okay. It's quite widely used. Some codes won't build with that, will only build with it. But the default optimization is pretty conservative, so you almost certainly want to crank that up. The AMD compiler is a bit more aggressive. It has some reasonable options, and as I said, Cray is even more aggressive by default. So message is here basically. If you're using the GNU compiler, you probably want to crank up the optimization level. If you're using AMD or Cray, then the default levels may be just fine. Okay, and so I'm not going to talk through this, but this is a sort of summary table of some of the important flags. Okay, so just to sum up, remember the compiler is always there. Try to help the compiler rather than doing its job for it. Use flags and hints as much as possible, and try to minimize the code modifications that you have to make. I mean, you almost certainly will at some point have to or want to modify code for optimization reasons, but you should at least think twice before doing it, and ask yourself: is this do the performance benefits really outweigh the software engineering downsides? Okay, good. Anybody got any questions? Okay, so we've got another break scheduled now, and then. Okay, so Barbara asked for the AMD processor. In her experience, is AOCC the best option? I think not, actually. I think generally we prefer Cray compilers. Yeah, but obviously those are not necessarily so widely available. So why no Intel compiler? Well, this is an Intel versus AMD thing. I mean, in principle, it probably would. You could probably get it to work. Yeah. I'm not certain, but my guess is that politics is intercompany politics is the answer here. Yep. So there certainly are some applications where not having Intel is potentially a downside, for sure. Yep. Yeah, as Adrian says, if you're dead keen, you can install it yourself. Yeah, but it's not really in Intel's interest to make their compiler work terrifically well on AMD processors. Okay, so the rest of the time, so take a break now. The rest of the timetable this afternoon is just for you to work on the practical exercises. We'll be around, obviously, but but if you want to drop out, then feel free. There's no more lecture sessions this afternoon. We'll resume those again tomorrow morning. So recognise that it's it's an hour later for lots of our European friends, so certainly don't expect you to stay to the bitter end if you don't want to.
So this is my screen on Archer. So I'm just looking at the Fortran at the moment, actually, which is quite nice to do because I've not done Fortran for a while. I've found myself stuck with C++ recently. And quite often we have people on courses. We don't have many people on the courses who do Fortran, but today we've had a few, so it's quite nice to have a look at. So here's an example of, this is the optimization 1 code. And as I said before, what we're really doing with these compiler optimizations is not really trying to test you and your skills, but just to try and demonstrate that we actually in a lot of scenarios, a compiler can do quite clever things and improve your performance. So this is a bit of stupid code that we've created here, which does lots of things here to calculate a number, but it's not particularly sensible. So actually, if you go through and read it, you'll see there's a whole bunch of stuff that's done here, which you can probably get rid of, and you can refactor down. And you can get rid of a lot of these temporary variables, and you can, as somebody said, you can make it 15% faster or 20% faster. You can go through this and easily, with a little bit of refactorizing this routine here, make it go faster. There's things you can do, such as, I here is actually really just going up with J, so you can replace I by some combination of J, and you can take out common sub-expressions here like C minus J, which is used in many places, and put those together. And you can see that B and E are collapsing together, so you have some of these things can factor out. And you can get rid of D and replace I directly into here. And you can take this really down to actually a very small implementation, which is a single line, which is something like, now off the top of my head, I can't remember, but it's something like A equals J times 6 plus 2 or something like that. And that will give you some performance improvements. But really, the nice thing to see is what the compiler does on it. So if I modifying my makefile. Now I know we say rather glibly, just have a look at the assembler, and I know that will not necessarily be first nature to anybody here. So let's have a look what this. Let me hide that there. What have I done wrong now? Yeah. So if I just compile now, well, let me compile with optimization level 0, and have a look at the assembler code that this has generated. Now, I don't expect you to know what's going on here, but what we can see is it does tell us a little bit here. It tells us about what lines we're on in the source code, and this is from file thread line 9 or file thread line 9, and you can see there's a lot of instructions going on here. So we have moves and jumps and substitutions and additions and subtractions and additions and multiplications, and so there's quite a lot of work going on in here. But if I compile that up at the O3 level and have a look, then we should see that the compiler gets a little bit more clever. So it's starting to do other things we've seen coming in here now. Okay, so there's things such as these vector instructions here, vectorization instructions. So these are using some of the specific hardware in the processor, and we've got these are vector registers that are being used here, and there's a little bit more stuff at the end here, but we can ignore that. But in reality, it's actually collapsed down that thread routine to a much smaller number of instructions here, which should run more quickly. And in some scenarios, you can compile this, I think possibly more in the C code than I've seen more in the C code than the Fortran, where the compiler will get rid of the code altogether and just replace it by an induction value, so a direct value, right? So the value that is calculated here doesn't actually change when we go through the loop, because A and N, these values up here, are fixed as parameters inside my program, and the compiler knows that, and it can go through and say, well, you're passing A and N in here, but actually that's never going to change. So I can substitute N for reps and N for this value here, and A is always 7, and because those things are never changed, I can push that through the code, and then I can take it down to a single value, and effectively it can get rid of this function called altogether and just say, A equals whatever it is, 13 billion something or other, and then print that out at the end. And so the compiler, now it struggles to do it if you don't make some changes to this code at the top here, but if you simplify this code down a bit, then it can recognize that some of these things can be substituted, and it will collapse them down. So it will collapse. Let me have a look. So here it's simplifies taking. Well, it's not running very slowly. We'll just see if we get a big difference in going up to. Now, in fact, it actually runs slower now. It's not a brilliant demonstration, but what I will do is I will set up a version of this where the compiler can demonstrate that it can do it more efficiently, and then effectively it can get rid of the calls to that function altogether, and this effectively becomes infinite, and the time becomes almost 0 when you do this. Now, it's not very Doesn't take very long anyway, but you still get the same result, and it can do it almost instantaneously. And in fact, actually, this can be quite problematic sometimes in performance optimization, particularly in teaching courses where you want small examples, because the compiler can sometimes recognize that actually you're not using data at all, and remove bits of code altogether, and then suddenly the thing you put in there to demonstrate performance disappears, and it's no use at all. It doesn't demonstrate anything. But it's the idea is that if you simplify the code sufficiently, then you help the compiler anyway. So we have these two ways of optimizing code. We can use a compiler, and it's a very sensible thing to do, and it's probably the place you should always start in optimizing your code. But even when you come to hand optimize the code and go in there and make changes, you generally are going to help the compiler do its job better. And the more you can simplify the code, the more you can help the compiler do that. And so there's sort of a win-win on both of these. But there's things to bear in mind, of course. Using a compiler or changing the code, you can change the results. So you need to be testing and have sensible test cases, and hopefully a test harness, which you can run routinely to say, yeah, okay, this is fine, or no, it's broken now, whatever I've done, I've broken. And then the other thing is, of course, what we're not doing here, but we should be doing is, if you're doing performance benchmarking, you really want to be benchmarking in a way where you get reproducible performance. So that means on the compute nodes, where you have exclusive access. Because if I run this this code here on the login node, well, it depends on how many other people are doing, how many other things people are doing on the login nodes and what else is going on. So you can see that the performance, the time it takes here, it's very quick, but it's varying every time I run it. And there's no stochastic nature to this algorithm. It should always be the same, but that's just because I'm running on the login nodes, which is contending with other people's work. So if you are doing profiling and benchmarking, you generally be doing it on parallel programs, so you won't be doing it on the login nodes, but you need to try and make the environment as reproducible as possible. And that on something like Archer 2 means submitting it to a batch system and running it there. And that's one of the reasons we have this short queue, which is like a debugging queue or a profiling queue on Archer 2, because you can then submit quick jobs there and get your results reasonably quickly rather than having to wait for the full thing. Likewise with the optimization 2 exercise, the idea here is that the compiler again should do your loop unrolling for you, but you can manually do this if the compiler is struggling to it. And effectively what you want to do is you want to take this loop here, which just loops through every iteration of our array and does some work. You can unroll it as it's shown in the example by doing something like this. Say every time I go around this loop, iterate, move the loop index 4, and then manually I unroll this in here myself, and make sure I access different bits of the array each time, and that's perfectly fine, except of course if n doesn't exactly divide by 4, then you have to put an extra loop at the end here to tidy that up, and then you could have now I think I could use I in both places here as well, but I'm always a little bit not confident that I won't overwrite my thing here, and then just change this to a J. Stupid. And so what this does is it just says, okay, what was the next iteration of this loop you're going to do? Is that below n? If it is, okay, keep going until you get up to n. So effectively, you get the remainder loop from whatever didn't fit into this loop here. And I'm sure, as Mark explained, the reason why unrolling can be beneficial is, of course, it's always doing the same thing here, but this loop, if you don't unroll it, you have to do you have to add 1 onto I, and you have to check if I is less than n every time you go around the loop. Whereas if you unroll it, you're now only adding 4 onto I and checking if I is less than n once every 4 iterations, effectively. pseudo iterations of a loop. So you reduce the overhead of this loop. Now again, the compiler should, for this kind of loop, the compiler will absolutely do this for you, and it can bring you some performance benefits. But there may be cases where you have more complicated loops, more difficult things going on there. The compiler doesn't understand or isn't confident it can do this automatically for you. So there is sometimes mileage in you manually unrolling loops like this. But in general, the compiler does this for you, and you shouldn't go there as a first resort. But if you've profiled your code, you've found this loop is expensive, and you've looked at the compiler reports, it's not something we've looked at yet, but the compiler can tell you what it's doing for its optimizations, and it's saying I can't unroll this loop, then that might be something you want to go do through and do manually. But of course, you can see the reason we don't want you to do it manually is it's a little bit nasty. It's more code here, it's more code to maintain. It's not as concise as it was. So it's nicer if the compiler can do this for us. Yeah. And then optimization 3 was starting to get into some of the things we'll look at tomorrow, which are things like loop orderings. So order we go for access memory, and actually the compiler 3 will do other, the compiler can do other things here, about like recognize that it's a matrix multiplication and replace it by a library call instead, which people said we were seeing happening in other of these optimizations as well. So the idea again here is that you can reorder these loops to access data in a more performant way and get some performance benefits. But the compiler can also do that for you if the loop isn't too complicated. So really, these exercises were just to try and demonstrate how good the compiler is, but bearing in mind that the compiler isn't always brilliant, so cannot always achieve things with complicated codes, with large codes, and so you may have to help the compiler by restructuring your code or by putting in compiler directives or things like that to help the compiler do that kind of work. Are there any questions? If not, then we can sort of finish the talk material here. There is another exercise on the practical note sheet, which is exercise 4, which is a more open-ended optimization practical. It's like what was done in the compiler optimization mini practicals, but it's a bigger, sort of more complete code, which has got lots of poor performance in it because it's been coded in a particular way to make it poorly perform. And so there's it takes quite a long time to run as it is, but what you could do is take it, compile it and run it as normal, and then compile it and run it with full compiler optimization on and see the performance difference you get. And then once you've done that, I'm sure your day will be up, but we can come back and look at it tomorrow, where we can apply some of the other things we're going to talk about tomorrow to that code.
Yeah, and if you are going to do that, just a hint that profiling it is very helpful. Great, thanks very much, Adrian.
My pleasure, Mark.
Okay, so if there aren't any more questions, then I think we'll wrap up for today, and hopefully speak to you all again tomorrow morning.